Hey guys, this is Academic Physics. We are in Unit 4, so we're talking all sorts of types of energy and how energy can be changed. So today we're going to introduce the topic of work. So what is work? So you might think of work as like homework, or maybe you work at a grocery store, so you're going to work. You might find this class to be a lot of work, but in physics, the actual definition, physics says it measures the amount that a force causes displacement. What do I mean by that is if you actually push something. So, ta-da, I have this stapler. I think you can see it. And if I push it, I've done work. Because the force and the displacement are in the same direction. So this is only when the force is parallel with the displacement is work done. Work equals force times displacement when they're parallel. So for example, right now, the work I'm doing is pushing this stapler up. It's counteracting the force of gravity. So if I go to the right or the left, I'm not technically doing any work because my force holding it up isn't related to the displacement. So in this, work, labeled W here, is measured in joules, which is also our unit of energy that we're going to talk about. F is the force that is parallel to displacement. I'm going to get more into that parallel thing later in the lesson. And D is the displacement in meters. Now keep in mind, displacement is your final position minus your initial position. So for example, if I start with my stapler here, I bring it up and I bring it right back to where I started, my overall displacement would be 0. And according to physics, I have done no work. Okay. So since work is in joules, force is newtons, and distance is meters, or displacement is meters, the joule, 1 joule, is the force of 1 newton for 1 meter. So if you pick up an apple, we think of an apple as a newton, and you lift it up for 1 meter, you've done 1 joule of work. Now, we talked about simple machines before. The whole point of simple machines is that they reduce the input force or the effort force, so they make things easier, but work is constant. So work, it might seem easier, but you're doing it for a longer period of time. All right, so let's do a sample problem. Let's say you're trying to lift a baby and it takes 80 newtons of force to lift. How much work is done if you lift the baby 2 meters? So work is force times displacement. So you always want to draw a picture. Now, for this one, you might be like, oh, it's so easy. I know, it seems simple sometimes, but I promise some problems are going to get complicated. And if you just draw a picture, it's going to make life easier. Okay, the displacement here is 2 meters. Now notice our force is up and our displacement is up. So they are parallel and in the same direction. So our work is going to equal our force, which is 80 newtons up, times our displacement, which is 2 meters up. So 160 joules. Let's do another one. Let's say it takes Superman 700 newtons of force for him to catch Lois Lane in the air. When he catches her, both of them fall another 0.5 meters. So how much work did Superman do? Well, work is force times displacement. So let's draw in the picture here. The force, him carrying her, is an upward force because her weight is going down and he has to counter out that weight to be able to carry her. The displacement, though, is down. It's negative 0.5 meters, and it's really key that you keep track of which way is positive and which way is negative. Once you realize that if they go down, even though his force is up, you're going to have a positive 700 force times a negative 0.5 displacement, and that's going to leave you with negative 350 joules of work that Superman did to catch Lois Lane. So this is a nice graphic, and it kind of goes over how much work can be done based on where the force is. So for this, if you notice, the motion is going to the right, the force is to the right, so the displacement is to the right. And so that's the maximum energy that you could add to the system. You are pushing something to continue its motion. Versus down here, if our displacement is still to the right, but our force is to the left, you're actually slowing something down. So that's the maximum energy subtracted. You're taking away energy from that system. You're taking away that kinetic energy from that system. So that's why we have negative work done. If you notice, if we go up on the force, but our displacement is to the right, you have not done any work. You have not added any or subtracted any kinetic energy as far as the displacement is concerned. And then the other guys we're going to get to right now. So if a force is not parallel with the displacement, we must only use the component of that force vector in our calculations. So you only want the piece of that force vector that is parallel with the displacement. So let's say we have this woman here and she is carrying or dragging her suitcase. Notice the force that she's applying goes like this, right? She pulls the suitcase. She doesn't just like push it on the ground. You would look very strange if you're at the airport and you were pushing your suitcase parallel with the. So the way we deal with this is we have to take apart just that piece of the vector that's parallel with your displacement. And this kind of makes a triangle if you see it. So this is the bottom piece of our triangle. We've got our force is the hypotenuse, or the opposite side of the right angle. So this is a right triangle. So our piece of the force that is parallel with displacement is F cosine of theta. And you can go review your trig functions if you need help with that to go over this. But basically, whenever you are looking at the side of the triangle that is right next to the angle and it is not the hypotenuse, then it's cosine. So like your coworker. So always take your force cosine theta. Now, if our force was parallel with displacement, then the difference, the angle between it would be 0, and the cosine of 0 is 1. So this works for all types, but that's just the general rule. So let's go ahead and solve one now. So we've got Susie, and she's pulling her suitcase with a force of 30 newtons at a 40-degree angle with the horizontal. So let's throw those in there. So we've got her force is going up here. Now notice her suitcase isn't actually like lifting off the ground and going in that direction. The displacement when you pull a suitcase is still parallel with the ground. So she does this for 15 meters. How much work has she done? So let's bring back that formula. So we're solving for work. Her force is 30. And then cosine of theta, so that's referring to the angle between the displacement and the force. So our theta is 40, so cosine of 40 times displacement, and our displacement is 15. Plug this right into the calculator as you see it. Make sure that you're in degrees, not radians. So if you get a funky answer, then it's probably your calculator is calibrated differently. So you'll get 345 joules. I think it ends up being like 344.7 or something like that. Remember, the number after where you cut determines if it bumps up or not. So before we do the next bit, I want to point something out. Let's say you have a graph and you're measuring force, and here's your displacement caused by the force. And let's say your line goes like this, right? Let's give these some numbers. Let's say this is 10 meters, and this is 3 newtons, okay? Some other number. Work is going to be your force times your displacement, and we're saying that all this displacement is caused by this force, so they're in the same direction. If I multiply 3 by 10, I get 30. If you notice, if you multiply this by that, what you get is this whole area. So work equals area under the curve. All right, so let's do an example like that. All right, so here's an example. How much work was being done on the object according to the graph? So when we look at this example, we want to find the areas under the curve. So we're going to divide this into pieces that are triangles and rectangles because those are easier to calculate the areas. So I've got one here, 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 and there. All right, let's go through it. So area 1. Area 1 over here is a triangle. So whenever you have a triangle, automatically put a 0.5 in front. Then we're going to measure our x distance. From 0 to 3 is a difference of 3. Then your y. From 0 to 3 again, so that's 3. 0.5 times 3 times 3 is like saying half of 9, so that's 4.5. Let's do area 2. Area 2 is a rectangle. You don't need the half for a rectangle. So you just need to figure out your x and your y and multiply them together. So this is starting at 3 and going over to 9. Between 3 and 9 is 6. And then up, you're going from 0 to 2, so 6 times 2, 12. Area 3, this is another rectangle, so you don't need a 0.5. You are going from 3 to 5 on your x-axis, so that's a difference of 2. And you're going up from 2 to 3, which is a difference of 1. 2 times 1 is 2. Area 4 here is a triangle. When you have the triangle, throw in that 0.5. You're going from 5 to 6 on your x, that's a difference of 1. And you're going 2 to 3, difference of 1. 0.5 times 1 times 1 is 0.5. Area 5 is again a triangle, so what do we need? A 0.5. And it's going from 8 to 9, so that's 1. And then here, the difference is the y is from 2 up to 5, so that is a 3. Half of 1 times 3 is 1.5. Okay, so let's look at area 6, which is a rectangle, so you don't need your 0.5. The length on the bottom, it goes from 0.9 to 0.10, so that's a total of 1. You multiply it by the height, which is from 0 to 5, so multiply it by 5, and that gets you 5. You're going to then add up everything here, 4.5 plus 12 plus 2 plus 0.5 plus 1.5 plus 5. You should get 25.5 joules was done on this object. Okay, best of luck with work. Let me know if you have any questions. Otherwise, I'll see you in the next set of notes.